Hurunui. Tonight's presentation has got a special relevance, obviously, to North Canterbury. In 2018, the Bragato Research Institute commissioned NIWA to do a report on the effect of climate change in Canterbury. This has recently been made public, and we're privileged tonight to have the lead author and a major contributor to that report to talk to us about it. What we will do is we'll let them make their presentations, we'll then take questions, and there'll be an opportunity afterwards for refreshments and an informal gathering. So I'm pleased to present Petra Pearce, who is the lead author of this report, and then we will have Andrew Laurie, who will talk after Petra. So Petra, if you'd like to. Thank you.
Try not to walk too far from the thing. Tēnā koutou katoa. My name's Petra Pearce and I'm from NIWA in Auckland. I'm the manager of NIWA's Climate, Atmosphere and Hazards Research Platform, and thank you very much for having us here tonight. It's really great to come along and be able to share the results of this piece of work that we did back in 2018. So I'm going to give a bit of a general introduction about climate change, and then dive into some Canterbury-specific results from this piece of work that's relevant to the wine industry. And then Drew will follow after that, and then we can take questions at the end. So why are we at this point where climate change is such a significant international issue? So since the beginning of the Industrial Revolution, around 200 years ago, we've had a large increase in the amount of greenhouse gases in our atmosphere. And the primary reason for that is the burning of fossil fuels, particularly in the countries that are more industrialised. So you can see in this nice animation here, you can see that the Northern Hemisphere emits more carbon dioxide into the atmosphere than the Southern Hemisphere, and you can see that some of those really industrialised parts of the world are really strong emitters. And carbon dioxide essentially heats our atmosphere, it stops the sun's radiation from escaping into space, and so then we end up with a warming climate. And you can see over time, so this graph on the top here shows thousands of years before present and the trace of temperature and carbon dioxide. And you can see that they go up and down quite regularly together. And so we've had this large increase in carbon dioxide, which is a greenhouse gas, in the last few hundred years, as you can see on the right-hand side of that graph, that blue line. And we're expecting, and we're currently experiencing, an increase in temperature as well, which will continue into the future. So what are we seeing in terms of evidence of climate change in New Zealand? So we've started to see changing patterns of our climate in the last few decades in particular. Since 1909, which is when our long-term temperature series in New Zealand starts, we've seen about a temperature increase of about 1 degree. And you can see that on the right-hand side here, this shows the average temperature anomaly, so the difference from average, over time from the 1900s down to the 2010s. And you can see over time that that anomaly, or that difference from average, becomes a lot warmer, and in fact 5 of the past 7 years have been among our warmest on record. So 2016 was our warmest year on record, and 2018 was our second warmest year on record, equal with 1998. We've also had our glaciers have lost about 30% of their ice volume in the past 40 years. We've had about 20 centimetres of sea level rise since the early 20th century, and that's a response of both warming of the oceans, and they expand as they warm, and melting of the ice caps. Marine heat waves have also become more common, so in the last few summers in particular, so the summer before the one that has just been and the one before that, we had quite significant marine heat waves around New Zealand, and those caused a whole raft of different impacts on our environment. And those are more common now than they were before because of climate change. We're seeing record or near record high temperatures being set almost every month throughout New Zealand. And also the pH of our waters around our country has decreased. So that's another sign of increasing carbon dioxide in the atmosphere. The oceans absorb that extra carbon dioxide and they get more acidic, so the pH goes down. So what may the future hold? Unfortunately, we don't have a crystal ball that we can gaze into to understand what we may be in for with our future climate. But we can do modelling, and that modelling can tell us about what we may be in for. And so we undertake this modelling on future climate changes using a range of different scenarios, and those different scenarios are based on projections of future greenhouse gas concentrations in the atmosphere. And those different greenhouse gas concentrations are related to different socio-economic policies, some that result in very low greenhouse gas emissions into the future, like the Paris Climate Change Agreement, for example, if all the countries followed that agreement, and other ones go more into the future in a more of a business as usual pathway or more extreme pathway with greenhouse gas concentrations just continuing unabated. So we use these different scenarios to do our modelling, and you can see that top graph there shows 4 different scenarios of future greenhouse gas concentrations, with the carbon dioxide up on the vertical axis and time on the bottom. And so you have more like that business as usual on the red line there, and you can see on the bottom graph here that that red line also results in greater temperature increase than say the blue line on the bottom, which is a lower greenhouse gas scenario. So at NIWA we undertake regional climate modelling downscaling to take global climate models, which are at a very low resolution, and make them a higher resolution over New Zealand. And so that process can allow us to understand climate change at a local level across the country, and that's the results that I'll be presenting here, which is that downscaled modelling that we've done. So I'm going to talk about 2 different greenhouse gas concentration scenarios tonight. One is what we call RCP 8.5, or a high emissions pathway, which is that red line, and the other one is a mid-range pathway called RCP 4.5. So just before I get into the projections themselves, I'll just talk a little bit about the work that we did with Bragato. So we ran climate change projections for 9 wine regions around New Zealand, from Northland all the way down to Central Otago. We produced projection maps for 15 different climate variables, so these include things like temperature, rainfall, humidity, wind, numbers of hot days, frosts and so on. I'm not going to present all of those different things tonight because that would just be really crazy, so I've just got a handful. We also did monthly projections from September through to April, so the growing season, so you can see the change in future projections at different times of the year, not just giving an annual picture. And we looked at 2 future time periods compared to the baseline climate. So we looked at the mid-century, which is 20 years centred on 2040, and we looked at the late century, which was 20 years centred on 2090. And so you can see how our climate is likely to change in the near future, so in that mid-century time frame, and then going out to that kind of 100-year time frame as well. As I said, we did this work for 2 of those greenhouse gas concentration pathways, so that mid-range pathway and the extreme pathway, so you can really see how the difference in potential future climate policies around the world may affect our climate here in New Zealand. So rather than just looking at one scenario, say the worst case scenario, you also look at more of a mid-range one to say, okay, well, if we as a global community go down this path of stronger mitigation of climate change, we may end up with projections that aren't quite so extreme. And this work is a basis for ongoing impact assessment work in the wine industry, and also adaptation planning in the wine industry. So you can use these projections to understand where you might be in 40 years or 100 years time compared to the baseline, and make some decisions based on that. So we produced a lot of little maps like this, and this, I'm going to show a few screens like this, so I'll just explain what it all shows. So this one is for average temperature changes, so it's a change relative to the baseline. Along the top we have the months from September through to April, and down the side we have the mid-century time frame on the top 2 rows, which is the mid-range pathway and the extreme pathway. and then the late century timeframe on the bottom too. So we've got the mid-range pathway and the extreme pathway as well. So this has changed relative to the baseline, and you can see that in the middle of the century we have around, so this is obviously Northern Canterbury, each little map, and I've got a zoomed in one in a minute, so don't worry about trying to squint and see what's going on. But it's a really nice way of just seeing how the trend goes when you have the mid-range pathway, which is your lower greenhouse gas emissions, and then the extreme pathway, which is your much higher greenhouse gas emissions, how that changes the temperature projections over time. So in the middle of the century we have quite similar amounts of temperature change for those two scenarios. And that's because at the middle of the century, as if I go back a couple of slides, and do I have a laser pointer? I do. So you can see here, this is our mid-century time frame. The scenarios aren't really that different in terms of their greenhouse gas concentration. But once we get out to this period, you know, the extreme one is up here, and this is our 4.5 is this one here. So you can see that there with the mid-century time frame is quite similar in terms of the projections, but by the time you get down to the end of the century, we've got quite a split in what those two scenarios are showing. So potentially, if I bring up the big picture here, this is the projected change in January average temperature between the baseline climate and the end of the century under that extreme pathway. And you can see there's a couple of local spots put on there, and the projections show that we're expecting around about 2 to 2.5 degrees, or between light yellow colour, 1.5 to 2 degrees of warming for January in this part of Canterbury. And obviously we get quite significantly more warming up into the hills inland. In terms of growing degree days, which is an important variable for the wine industry and horticulture in general, we also see increases across the board. So we see the largest increases in the summer months, as you would expect. So we've got these December, January, February kind of months here, which show the largest increases. And again, you see that same pattern of similar changes in the mid-century of around about 20 to 30 growing degree days per month. And by the end of the century, you see a much larger division between those different scenarios. And again, I'll bring up a larger picture here. So this is the change in the number of growing degree days in an average December between the baseline climate and the end of the century under that extreme pathway. And so you're potentially expecting around about 50 to 75 more growing degree days than you experience now. And so to put that into context, we did a wee calculation here of the total number of growing degree days. So this probably makes more sense to people that know about growing degree days. You look at it as a total seasonal amount of about just over 1,000 or just under 1,100 under the historic baseline for this part of the country. And under that mid-range pathway in the middle of the century, that's projected to go up to about 1,200. So this part of the country around Waipara is potentially going to become a bit like Burgundy or Alsace in terms of the temperature regime around average temperatures and growing degree days. And again, for the extreme pathway at the end of the century, going up by almost 500 growing degree days per growing season. And so Waipara may become more like Hawke's Bay in terms of its climate and temperature terms or in growing degree day terms. Of course, the caveat is that that's just looking at growing degree days, not at things like rainfall and humidity and that kind of other things that are very important for grape growing as well. But just to give you an indication of the scale of those potential changes. In terms of hot days, so this is days where you have temperatures above 25 degrees. I thought it would be useful to have the baseline climate maps in here as well. So you can see that at the moment, the Canterbury area gets most of its hot days in the summer, as you would expect. And in the future, so if you look at this, at the moment, the bluey kind of grey colour is no hot days at present. So in the spring and in the late autumn, you don't really get those hot days. And in the future, we're expecting the hot season to increase in length, basically. So potentially you can see this kind of trend of, by the middle of the century, you're getting more hot days, potentially more hot days, particularly going out into March, the late summer period, and then by the end of the century coming into this early spring period as well, and potentially increasing. So this is monthly numbers of hot days as well. So remember, you have 30 odd days in a month. In the present climate, you have around about 10 to 12 hot days on average, and then by the end of the century, you've got over double that. And just a point about these is that at a local scale, you probably get more than that amount of hot days in a certain location. But the resolution of these models is at a 5 kilometre resolution, so it's not going to pick up the really specific kind of local scale terrain and things like that that affect local scale temperature changes and those really extreme temperatures as well. So it's just interesting to see that that expansion of that hot season really. And there again is that large image there, so you can see that quite large increases, particularly as you go further inland as well at higher elevations. Increasing too. And this is some nice graphs that show the changes to the number of frost days or the duration of the frost season. So we can expect to see a shortening of the frost season. So this is this top left graph here. So at the moment, the blue shows the historic baseline, or the period from the early 70s until 2006, which is when our future projections start. And you can see that we're around about just over, say, 110 odd frost days per year, or the frost season duration, sorry. So the duration from the first frost to the last frost is about 100 odd days. Of course, there's a lot of variability in that, which you can see from that shading either side of that line. In the future, under those different scenarios, so remember again that the RCP 4.5 is that mid-range scenario and 8.5 is that extreme pathway, you can see that the duration of that frost season decreases, particularly under that extreme pathway. So we're likely to see a shortening of that frost season in the future. Also, the number of frost days in total is likely to decrease, so particularly under that extreme pathway as well, but also under that mid-range pathway. Interestingly, that mid-range pathway kind of goes down and then it flattens out towards the end of the century, and that's because those greenhouse gas emissions kind of flatten out as well. In terms of the dates, the start date of the frost season, we also see that date getting later, so you can see the months up on the vertical axis here. So getting later into winter before you get your first frost, and slightly earlier into spring or late winter when you get your last frost. So that's, again, that shortening of the frost season potentially. But again, you can see, if you can see that shading either side of these solid lines, there is still a significant variability from year to year in those frost projections. So some years you may get not many frosts at all in a warmer year, and some years you may get a lot more frosts as well. So it's not a straight line, and you're also not going to get year-on-year reductions in frost. So you might have a few years where it's warmer and then colder and then warmer, colder, but that baseline is changing. So as climate change kind of goes on, and we have those changes to our average temperatures, the likelihood of getting more frosty conditions is going to go down because that baseline is changing. So in terms of rainfall, it's quite interesting to see what's happening here in Canterbury. So you can see that there's a lot of variability. So the warmer colours show a reduction in rainfall, potential reduction in rainfall. So it's a percentage change on the right-hand side. You can see the little colour bar there. And the cooler colours, so the greens and blues, show increases, potential increases in rainfall. So it's quite patchy across much of the region, and depending on the different months. But you can see some general patterns in terms of potentially increasing rainfall for this kind of spring period or mid-spring, and then reducing rainfall in kind of November, December period, with more red colours, and then increasing again for maybe late summer. So if we're looking at the Waipara area here, and then potentially decreasing in March, and increasing again in April. So it's, you might see some quite different patterns in terms of rainfall depending on the month of the year that you're interested in. And again, I'll bring up that large map here. So this is January, percentage rainfall change under that extreme pathway at the end of the century. So you can see that there's, obviously this band of potentially increased rainfall, including Waikato here, up to, maybe 15% more rainfall in any given January on average. One of the signals with climate change that we understand relatively well is changing intense rainfall, the intensity of rainfall events. So with a warmer atmosphere, that atmosphere can hold more energy and more moisture, and so when it rains, in terms of heavy rainfall events, more rain is likely to fall out of the atmosphere. So we're likely to expect more rain when it does fall, so particularly in those really short duration events, which this graph is a bit complicated to explain, but you have a percentage change in rainfall depth per degree of warming. So say we have 2 degrees of warming, you could double this percentage change, and you have the return period of an event here. So the ones at 100 years are rarer, so that's like your 1 in 100 year event compared to your more common events. And then the different colours correspond to the different event durations. So this graph basically shows that shorter durations, so the blue corresponds to a 1 hour event, and the brown down the bottom corresponds to a 5-day event. The rainfall intensity is going to increase more for those shorter duration events than for the longer duration events. So for things like really short, sharp downpours, the percentage change in the rainfall intensity is going to be larger than, say, a 5-day storm, the amount of rain that falls in a 5-day storm. So you can see here that we have, for a 1 hour duration event, we have a potentially increasing amount of rainfall that's falling of about 12 to 14% per degree of warming. So say if we get 2 degrees of warming, it's double that. Whereas for a 5-day duration event, it's only 5 to 6% increase. Still an increase, but still gonna, we're still gonna feel it, but it's not going to be quite as pronounced as for those really short duration events. So I've got a little example here for Christchurch. At the moment, for a 100-year return period event, which is a very extreme 1 hour rainfall, so that's a very, very extreme rainfall event. At the moment, the baseline is about 30 millimetres of rain that would be likely to fall in an event like that. Under that extreme pathway at the end of the century, that same return period will likely produce 41 odd millimetres of rain. So it's it's kind of loading the dice in a way. It's changing what we expect in terms of the amount of rainfall, and then obviously the designs that we base our infrastructure on is on our baseline, and so the impacts associated with that increasing intensity of rainfall will change over time.
The current 100-year at 30 mils,
Yep.
what does that return period reduce to?
Good question.
That's known.
Good question. I would have to work that out, but I can work that out and get back to you on that. So on the flip side, in terms of drought, we use an indicator called potential evapotranspiration deficit. And so that's essentially the amount of water that is needed, or the amount of rainfall that is needed to bring soils up to field capacity. And so it's measured in millimetres, and we can see here that, so the redder colours are where that deficit increases, so you need more rainfall to bring your soils up to field capacity. And you can see that for the summer, for some areas, so particularly those inland areas, Banks Peninsula and places like that, that drought potential is increasing. But again, it's patchy, and that's because of that rainfall patchiness that I was talking about before. So particularly in the late summer period, you can see here there's a few blues and purples and things, and that means that there's just not that much change in the drought potential, and that's because we have the rainfall signal is kind of outweighing the temperature signal. So when you have temperatures causing more evapotranspiration or evaporation into the air, when you have warmer temperatures, but we've got rainfall compensating for that, extra rainfall compensating for that. So yeah, that's an interesting signal there. And there again, we can have a large picture there. So it looks, I guess the colours on this, just to note, the blue is not like it's getting really wet in terms of PED, this indicator. You can see that it's only 5 to 10. So we kind of think around about plus or minus 30, 20 to 30 is not really that much change. So yeah, there's probably not that much change going on in terms of drought potential under these projections. So just to recap before I finish off, we have generally increasing temperatures over time and increasing numbers of growing degree days over time. We have more extreme high temperatures and potential for heat waves. We have fewer extreme low temperatures or frosts. There's a general decrease in spring and early summer rainfall and some increases for summer and autumn, but again, it's quite patchy. The potential for larger extreme rainfall events or more intense rainfall during those events, and minimal change to drought potential overall. So in terms of the wine industry, what may this mean? Changing harvest times and durations. So because of those warmer temperatures, things may ripen faster and get going faster. Winters may be shorter. You may have fewer frosts on average, which could be a good thing, but then also may not be such a good thing in terms of increased risk from pests and diseases. There's also a change in demand for water resources with that changing timing of rainfall through the year and also those intense rainfall events. With the changes in temperature, you may have the opportunity for new varieties that can't currently be grown here, and also potential expansion of vineyards into currently marginal areas that are marginal for climate reasons. It's also important to note that other countries will be worse off than New Zealand in terms of climate change, so we're not going to get the 50-degree days or the endless droughts and things like that that, say, Australia may be in for. So relatively speaking, we're not going to be the worst off, which is a good thing. So that's it from me. Thank you very much. I'll just hand over to Drew for his piece now, and then we can take some questions at the end.
Kia ora koutou. This is just a brief overview and update of a project that is supported by MB to derive some new types of seasonal climate forecasts for different areas of New Zealand, particularly in agriculture and industry. And we're using machine learning, otherwise known as artificial intelligence, to do these forecasts. And I'm presenting this on behalf of colleagues in Auckland and other institutes in New Zealand. So just briefly, NIWA every month produces a 1 and a 3 month outlook for temperature, rainfall, river flows, and soil moisture. And that's based on getting together a consensus of global climate models and saying, what does it mean for these larger regions of the country? And more variables from these types of forecasts are possible, and we couch things in terms of probabilities, whether you're going to get above normal, or below normal rainfall. And we also take into account global climate drivers, things like the El Nino Southern Oscillation. And what it does is basically takes a view from a large-scale global climate model and provides a national-scale context for what the outcomes are going to be. But I know what you're thinking, because I'm thinking it too. Where the heck is my paddock on this map? Where's my vineyard? And so that's the main problem with these types of outlooks in the past, is that their local relevance is somewhat limited. And we think we can improve that by taking a global climate model and how that sees the world. So this is how a global climate model sees the planet. It divides it up into grids, and of course they're very, very large, covering in some cases hundreds of kilometers in terms of resolution. That's really not any good for somebody who's sitting up in a valley somewhere trying to grow grapes. So what we're going to do, though, is we can actually look at these global models, and we can take the traits that we see in them and their patterns, and we can correlate them in some special ways to climate stations that we have on the ground in local conditions. So we can actually run a calibration between this large-scale model and all the information that's contained in it, which is a lot of information, to somebody's weather station that they've been running for years and years, thereby surmounting this issue of resolution that we have in the global climate models. I might just add here that the global climate models are actually pretty good. They get a lot of the characteristics of the general atmospheric and ocean circulation of the planet pretty good, and they're used for predictions of things like obviously like marine heat waves, and I think for rainfall and temperature in many places they're very good. But again, for a place like New Zealand, which is relatively small, maritime climate, and has a lot of undulating topography, we want to try to do a lot better. So we had this idea, and we got some funding from MB to trial this approach. And we ran a series of consultations over the last year and a half across different industries, including the wine industry. We collaborated with Bragato, and we had a couple of sessions with people, and we decided on some case studies to demonstrate how this approach would be lined up and work. So effectively, what MB is paying for is all of the research and development of how we do this method, which is normally prohibitively expensive. Somebody who is a practitioner who has a 3-hectare vineyard is not going to be able to afford $1 million project to explore this, because we just don't know how it's going to work. So MB's paid for it, which is great. So what we did is we looked at various industries, and I'll be really honest with you guys. The cutoff for inclusion for some of these players is a $1 billion industry. So wine automatically qualifies, right? What we decided on was looking at 2 places for viticulture. We're looking at the Innovation Vineyard in Marlborough, and we're running a calibration in Cromwell, basically right where Wooing Tree Vineyard is. So two different regions where we've got 2 different vineyards. We're also hooked up with apples and pears in Hawke's Bay, in the Hurunui Plains. That's also very close to some vineyards, so we think it has some application there. And we're looking at a couple of catchments up in Auckland, which relate to the local water managers up their water care. We're looking at different scales as well. So for the Innovation Vineyard and in Cromwell, that's essentially a paddock scale exercise, scaling it towards very small areas. We're going slightly larger in the Hurunui Plains. We're looking at essentially large parts of the river valley. And up here in Auckland, looking at the Waitakere Ranges and the NIWA Ranges, we're looking at catchments where there are reservoirs, and trying to improve those forecasts. So it was a consultation with many of these parties, getting in a room and also figuring out what climate variables they wanted to see in a seasonal climate outlook, and in terms of what would it mean if we got this forecast right 3 months out, what sorts of decisions would be made using that information, and how basically it would save you money. We're still trying to learn about that. This is just a brief update, okay? So that's basically my part of the presentation. And what I want to say here, this is a graph of growing degree days over 2017, 2018, which many of you who grow grapes would remember. That was an absolutely incredible year with a marine heat wave in the Tasman Sea, and it drove temperatures up, some of our warmest temperatures we ever had. And people were harvesting Pinot Noir in Central Otago in late January. Now, I don't know about you, but I don't want to be doing that regularly. But the point of this type of exercise, or this graph here, is that climate change in 40 years and 80 years' time is going to raise the mean climate state closer to some of these levels. And on top of that, you still have seasonal climate variability, the year-to-year variations in your seasons, that is going to go right on top of that. So you still have to keep an eye on what the year-to-year variation in your seasonal climate patterns are going to be. And that is what this project is focused on. We're going to be completing the method by early next year. We'll have information to report back. So far, so good. It looks pretty good. We'll be geared up to make bespoke outlooks for different industries, and we're talking with our research institute, just talking with Len Ibbotson about this. He's new at Bragato, but we've been recently discussing what an industry level tool would look like, where we could get this information in something like an app, where people will be able to access it and use it and make decisions with it, make their lives easy. And from that, what I think is interesting is that if you're forecasting for things like temperature, rainfall, and things like growing degree days, you can start considering having bolt-on models, things like phenological models, crop yields, harvest timings, and start talking about, okay, what are the pressures around my workflows and about my business for that season, and how do I strategize around that planning. So we're looking at that. We would love feedback from industry members, from farmers, from viticulturalists about how this sort of technique could be useful for your lives. So please get in touch with me if you would like more information and like to be kept abreast of our findings when we're completed, and talk more about how it can be implemented for you and your community. Thank you.
What does phenological mean?
Pardon?
What does phenological mean?
Oh yeah. Where's Amber?
The developmental stages of any species. So, you know, plant phenology, we've got flowering, grapevines, raisin, insects also have phenology, birds have phenology. Yeah.
So people see some stages. My limited understanding is that they see certain signs from the plants, and then from that they're able to say, okay, in X number of days, I expect to be able to do this activity. So those sorts of models that they're wanting to use with our forecasts are valuable, I guess, for planning.
Thanks, Andrew. Are there any questions for Petra or Andrew that people would like to put?
Yep, it's interesting the picture that you talked about where it shows slides of this area getting wetter in January, February under climate change, and that sort of is a bit different to what a lot of the other modelling or other people would say that generally like the East Coast or South Wales is going to dry. So how do you work out if this area is going to be wetter?
Yeah, so there's some, should I put this thing back on?
Please.
Yep. There's some interesting different signals for different parts of the country that aren't necessarily as expected. So we see clear trends of wetness for the West Coast in particular and Southland, and clear signals of dryness in the East and North Island, so Northland and the East Coast of the North Island in particular. The rest of the country is quite variable in terms of those projections, and if I just go back, we'll just look at those maps again. You can see that most of the changes are in that kind of green and yellowy kind of space, right? And that's only plus or minus 5 to 10%, and this is on a monthly scale. So they're not massive changes that we're talking about here, and so that's why I kind of made the point that it is quite variable, particularly for this region. If you were looking at the maps for the West Coast, you see much larger increases, so well more than 20%. You know, winters under that extreme pathway are going over 40% more rainfall for the West Coast. So that's just, yeah, there's some signals there that we need to dig more into in terms of what's happening in certain parts of the country, and I think Canterbury is a really interesting place where there's some I think some of the effects in the actual modelling, the spillover of the Alps and things like that, in terms of the physics of the models, there's a bit more work to do in that space until we really understand what's going on. But it gives you an idea of some potential patterns.
So just following on from that a wee bit, are you expecting to see a change in where our weather's coming from? Or is this just more of the existing sort of pattern? So we're going to see, currently we don't get a great deal of northwest rain. Are we going to start getting northwest rain, or will it be easterly rain?
So that is, it's a really good question, and it's something that we at a general scale understand, but at a local scale we still need to kind of do more work into that. So in terms of those weather patterns for Canterbury, I can't say much about that, but in terms of the overall New Zealand situation, we're expecting an increased westerly flow across the country, and that's mainly because of a compression of the westerly wind belt around the southern hemisphere. So we get an increase in the subtropical high pressure belt moving further south, and because of that we get a compression of those westerlies that go around the southern hemisphere. And so that's why you see, for the west coast in particular, that increasing rainfall from that orographic rainfall effect. That at the moment they get lots of rainfalls because of that westerly flow, and if we're getting increased westerlies in the future, we're likely to see more rainfall because of the increased westerly flow. We're also potentially likely to see tropically derived systems through more intense tropical cyclones and things like that. But yeah, the local Canterbury scale, I think that's something that we need to look into more, and it's there's lots of research going on in that space. So yeah, thank you. Yep.
If you had a magic wand, what would you have as parts per million?
A magic.
Carbon. If you had a magic wand, what would you dial the carbon levels at?
Yeah, 350.
350.
So we're at 410 or something, I think, at the moment. Yeah, so we're two. Yeah, we need to come down from that, ideally. But, yeah.
I'm not going to say 180, which is the last glacial maximum. That would be great.
Yeah, there wasn't much there at 350. Most of it looked like 300 and below on your chart.
Yeah, correct, very industrial, but to actually get down to that level, it's a very hard ask at this point.
In your extreme pathways, looking at the mountains called the Alps, it seems like there's quite an increase in temperature over those sort of summer periods and a lot drier. And just wondering what you think the effect of that will have on our nor'westers, because we have quite strong nor'westers in summer.
That's a good question, and I actually have no idea. So that's again something I think with that local scale weather pattern thing. There's a lot of research that's yet to be done in that space. So yeah, good question though. Thank you. Yeah.
And as far as total crop records go, do you have any hail predictions? Or would we expect more with the erratic weather? It would be natural that we would get more.
That's a really good question. So with the kind of scale that our models can go down to at the moment, like I said, it's a 5 kilometre resolution that these projections are at. But the actual parent models that we use are about 250 kilometres that we downscale to about 27 kilometres. And so they're just not precise enough to be able to capture things like those convective thunderstorm type events. They don't even capture tropical cyclones very well. So, and tropical cyclones are hundreds of kilometres wide. So in terms of things like hail, tornadoes, thunderstorms, that kind of thing, it's really hard to say what, in terms of any specific projections we can make. We can make some kind of statements to the effect of, if we have a warmer atmosphere, if that atmosphere has more energy, we could expect more convection in those kinds of thunderstorms, which may influence the amount of hail or the size of the hail. But in terms of any actual measurements or projections on, you might expect your hail to be this much larger, or going from this size to this size. We don't have that information at this stage from what I'm aware.
The work that we're looking at is based on a collection of climate models.
Yeah.
How many models do you have in the pool that you're consolidating? And do you sort of consolidate them? Or,
yeah.
And the models come in and out of the pool as they...
So for these projections here, we have 6 global climate models, and those 6 models were chosen from the suite of about 40 that the IPCC, or the Intergovernmental Panel on Climate Change, have in their package, the CMIP package. And those 6 models were chosen by our modellers because they represent the New Zealand situation the best when run in the past mode. So when you look back at the past and you compare the model past with the observed past, so we look at actual observations of the past, those 6 models perform the best. And so we use those 6 models for the downscaling and to generate these projections, and then we average those 6 models together. So that captures kind of the best estimate of the future predictions for those 6 models.
The other thing I mentioned is it would be lovely to have the remaining 30 models that were in that suite together with this, right? But it's incredibly expensive to do this downscaling exercise. It's a very cost and time intensive exercise. So because of our very narrow budgets to do this type of stuff, we had to choose.
Which is the best model?
That's a great question, and I am not the person to answer that question.
They all have, like, a way to think of it is like they all have their merits and they all have their deficiencies. And by taking an ensemble of at least 6, you're never reliant on one model in one situation where that might be deficient. So you're counting on the strength of all 6 to sort of overcome those sorts of situations.
Now, are they all from the same, like, are they all NASA models? Or?
No, they're all from different.
All different.
Yeah, there's
all
like
different
UK,
countries,
I
universities.
think there's a couple of US ones, a Norwegian one, a Chinese one, from different institutes around the world.
But when they're set up, Andy, 1 second. When they're set up, they use inputs that are common. So they use things like the greenhouse gas forcing that's common, so that they're what's called parameterized when you start the model off and when you spin it up. They all have, because they're part of this suite, all of the experimenters agreed to start their experiment using a certain set of conditions that they put into the model. And the models have to be based in physics. Some of the things that are in the models are tuned a little bit differently in terms of how the physics works, but basically they represent how the planet works very well. Yes, Andy?
Just going to add a little question related to models. Quite a background in models. If you could actually look at the variability within the models to give an indication of uncertainty. So if they all agree on what's going to happen in, say, 2040 for temperature, then you can think, well, I'm pretty confident that's going to happen. But if they all disagree, then you've got a certain amount of uncertainty associated with that estimate. So you can probably say a little bit about the way uncertainty is basically built into these modelling exercises.
Yeah, so essentially we have the different models that we use, in terms of temperature. They're all going in the same direction. They're all in agreement that temperature is going up into the future. The range of temperature increase does increase over time in terms of that uncertainty because, like Drew said, the models have different physics and they're tuned slightly differently. So they do come out with slightly different results. In terms of things like rainfall, there is a lot more uncertainty, particularly in somewhere like New Zealand where we, are an island sticking up out of the ocean. So the physics in those models aren't quite as certain over this part of the world. And I think in general, rainfall isn't as certain as, say, temperature. But for now, it's the best information that we have, and we're constantly improving with the resolution and the numbers of models that we use to try and make more robust projections for the future.
The data that you use for your models, does it include data from what we hear about, internationally around tipping points across Petra and so on? Does it include any data connected to those? And if it doesn't, how do you see those affecting
The concept of a tipping point that you would see in a model, when you run a model, you can adjust certain things in it. So, for instance, you can adjust the concentration of CO2, and you would say, okay, well, what occurs to an environment, for instance, if I raise the temperature by 4 degrees? So the tipping point, there's things that you look for in response in the model of where it will go and where it will stay after you've reached that point. To go to the heart of your original question about what do the models include, they are coupled atmosphere, ocean, general circulation models. So they represent the physics of the fluids of the atmosphere and the ocean very well, how that works together, how they exchange information up and down and side to side. There's varying complexities of, for instance, ice sheets and how ice is represented, how sea ice is represented, how vegetation is represented, how the carbon cycle is represented in some of these models. And that's what makes some of the results different across the clearinghouses that produce this information. But they all have this underlying set of information that is fed into them in terms of things like CO2, methane, solar radiation, etc., that they can start from a common starting point and then give us an answer. And the modeling that was done 35 years ago, it didn't have a lot of these components that I've just said. It was a lot more simple. So that they're increasing in their level of complexity in the models, and therefore the feedbacks to the climate system that you get when you perturb it with things like CO2.
Given that we don't seem to have any international leadership around climate change with pulling out of the Paris Accord and things like that, are we looking at basically 20 years, not long, mid-range pathway or extreme? What's the realistic position?
So, by the middle of the century, those pathways are still fairly similar. It's only really going to be around about 2050 that we start splitting off. Obviously, before then, we need to be on track to go one way. You can't just split the switch and go down to that lower end pathway. So that's part of the potential issue with climate change action is that it takes a long time to actually see the results of the emissions. So the climate that we're seeing now is forced by emissions decades ago. And so the emissions we have now, we're not going to see those impacts for another few decades. But by then, we're already seeing those impacts in terms of marine heat waves and ocean acidification and stuff like that. So, that didn't really answer your question, but
I think an important part to add to that, Petra, is we know where we want to get it to, and Petra's right that we're on this common pathway right now before things diverge. And a different way to look at it is that the amount of time that you'll have to change that path back is going to be shorter, and the cost is going to be higher, and your ability to get it to that path is going to be harder. So we have choices that we can still make about what path we go on and how quickly we get there and what the cost to us is.
An item on the radio today suggested that a lot of European countries have reduced their greenhouse emissions, whereas New Zealand keeps going up and up and up. Where would be the best place for us to attack to reduce our emissions?
part of the recent reductions in places like Europe and the UK have been from their phasing out of coal. We don't have a lot of coal, so we're kind of starting from a baseline that, you know, we already have 80-something% renewable electricity. So, you know, we're already in that good position in terms of we don't have a lot of coal to phase out. Of course, if we can phase out more, that would be great, but that gets harder at the time, I guess. Sorry, what was the second part of your question?
Where would be the best place for us to emphasize to reduce our greenhouse emissions?
The key one is probably transport. So, you know, we can start to switch our transport fleet to electric. That's gonna help in a huge way.
And our government's got no incentives the way Norway has in other countries?
Not at the moment, no.
We just aren't going for it.
There's also been a lot of discussion around agricultural emissions in New Zealand as well. Yeah, all of the industries that we have. And there's some really tough conversations to have around that, about the implications of dealing with that, the costs to people who are working on the ground in their lives, and also what the outcomes would be if we don't do it. So that's probably another area. Andy, did you want to add anything to that?
Methane is our main problem. That's our main contribution to global warming per capita is methane. It comes from animals, particularly farm animals. So we're in a bit of we can't do what the Europeans have done and just reduce, converting from one form of energy to another. We can't change from that. Well, they are trying to change from certain types of animals, and they're trying to breed animals that produce less methane, so they are making efforts in that direction. But methane is the thing that we're known for.
You mentioned the cost Who's your favourite climate economist?
What's my favorite what?
Who's
Climate
your favourite climate economist?
I'm an economist.
Because the cost part is a big part of it.
I'd say I don't have one really. The people that I sort of pay attention to are probably more climate scientists who would make the handshake with your economists, so you people who are dealing with risk related to the implications of climate change. It's a good question. Can I think about that for 5 minutes and talk to you over cake?
So Canterbury's going to look like Hawke's Bay in 2040 or 2070 or wherever. What's Hawke's Bay going to look like?
Should have brought those numbers with me, but it essentially gets, further north, so Northland-ish.
So does that mean they're growing bananas? Or does that mean
Maybe.
it's too volatile to...
No, maybe. I mean, look at the tropics. They grow all sorts of great crops in the tropics, and we're involved with a lot of research that looks at future crop suitability based on these projections and other pieces of work, what kind of crops could be grown in certain locations around the country. And we've just done a piece of work for Kaipara District Council up in Northland to say, what are the future projections there, and what could potentially be grown there, and things like peanuts and soybeans and avocados. I mean, obviously avocados are big at the moment, but those kinds of peanuts and soybeans and things like that, you don't think about growing those things in New Zealand at a large scale. But in the future, absolutely, potentially, based on increased temperatures and changes to our rainfall patterns, there's a large opportunity for new types of crops, and that is valid for the whole country as well.
Well, perhaps just to expand on that soybean conversation, New Zealand grows bugger all, and quite frankly, I don't think it's ever going to solve the world's food problems as far as soybean production goes. But countries like Argentina perhaps can and do now. What happens to them?
In terms of their
In
future,
terms of, and where they're looking at it. So where's the food production going to come from? That where it's happening now, where's it going to move to?
I think there's only there are constraints on arable land that you got to consider first. And so in addition to what Petra said in terms of opportunities for new varieties or expanding into grapes that, for instance, you wouldn't dream about trying to grow now, but you could under a warmer climate. The other side of the coin is that there are mechanisms to defend against some of those impacts from climate change. So, for instance, how are you, for viticulture, how are you managing your vines? How are you managing the ripening process? Are you protecting them from the sun? How are you protecting them from disease? I think managers of farms and vineyards are going to be clever enough people to learn how to adapt and to use tools at their disposal to deal with some of these issues right away. So it's not going to just be, oh my God, I have to swap out my grapevines for whatever this crop, or change my pear trees to something else. I don't see a wholesale swap out in many ways. I think that there's going to be a measure of thinking about the problem and saying, how are we going to adapt to the impacts that are on the horizon from the changing climate?
Is that advice going to come from the Ministry of Primary Industries in association with you guys? Where does that advice to land users come from?
I think our role is to provide this evidence. What do you think? We provide the climate evidence, and there are a whole bunch of other people who will take that and know how to use it, know what to do with it, know the type of guidance to give industry. And that's, I think, one reason why Bragato, for example, engaged us. And there are other industries that are engaging us for these data that then they're taking on and using for decision making.
Lincoln did work on grain legumes in the 1970s for Canterbury.
Just getting back to January, February being maybe a bit wetter, will that mean increased humidity? Have you looked at humidity?
Yep. Yes, in general. Yep. If you've got a warmer atmosphere as well, increased humidity as well.
So that'll be right throughout the food.
I can't remember off the top of my head, but if you look at the full report, all the maps for humidity as well.
Are people here able to access the report? And how do they access it?
It's the Bragato.
Was Daryl?
Daryl?
Hi, so I've recently joined the Bragato Research Institute as one of the principal scientists. The report, as you said, was commissioned 2018, so it's now being rolled out to the industry. The intention definitely is to make it publicly available, so this is part of that process, presenting it as well. But yeah, I'm absolutely caught up to very interested in seeing the data and timelines on it.
So when you're using the model, can you actually try in that with things like with local adaptation for each?
So for when we do the kind of initial downscaling, there was some work that went on to look at the historic runs of those models. So those models go back in time, basically, and how that compared to the actual climate going back in time as well. And so that was part of the how we got down from that list of 40 models down to the list of 6, because the 6, they worked the best over that historic time frame.
Right. If there are no more questions, I'd just like to thank Petra and Andrew for a very illuminating presentation. And as we're saying, the report will be available. It's quite long. But thanks very much. And in our normal fashion, we will reward our speakers with a homemade cake, but that comes later. We'll have an opportunity for some refreshments and an informal chat. I'd just like to remind you that next month, on August the 20th, we have Dr. Nicholas Craddock-Henry, who will be talking about exploring future adaptation options in terms of climate change and how to get there. So that's a month's time, the 20th of August, here. And it's part of a